So in this first question of the third homework assignment, we're given a probability question. So in 1980, there were about 3.6 million births, and of which 68,339 were to twins, and 1,337 were due to triplets or more. Okay, so the first part of this question is asking about the probability of having multiples or more in 1980. So that is just going to be the number of twins plus the number of triplets divided by the total number of births. Okay, and if we do this math out, that's going to give us about 1.93%. So that's the probability of having multiples or more in 1980. So that number is going to be used in the next few questions. So I'm going to save that number. I'm going to rewrite it up here in the corner so we don't forget. So let's take a look at the next part of this question. So the next part of this question reads, what was the probability of a woman giving birth to multiples twice in a row? Okay, so if the probability of giving birth to multiples is 1.93%, having that happen twice in a row is just 1.93 times 1.93. Okay, and that's just going to be 0.00037. So this is the probability of giving multiples twice in a row. Another way of putting that is to say 0.037%. So the last part of this question reads, if a woman had 10 births in her lifetime, what was the chance that at least one of those births was to multiples? Okay, and we know this is an at least question because of the wording in the stem. And I'd just like to remind you that for these at least questions, right, the trick is to realize that the probability of the event happening at least once is equal to 1 minus the probability of the event not happening at all. Okay, so the probability of having multiples in one birth, we know from the first part of this question, is 1.93%. So therefore, the probability of having no multiples, right, is 1 minus 1.93%, or 0.9807. Okay, and then so that's going to be over 10 births. So what we want to do is raise this number to the 10. Okay, and that's going to give us 0.8229. Of course, then the last thing we want to do, because this number represents the probability of no multiples over 10 births, we want to do 1 minus that to get at least one multiple, okay, for over 10 births. So we're going to do 1 minus 0.8229 to get 17.7%. Okay, so if a woman gives birth 10 times, the probability that she's going to have multiples at least once is 17.7%. So the second question reads, suppose that the probability of surviving for 5 years after being diagnosed with a cancer is 0.6, and the probability of surviving for 10 years is 0.2. Okay, that's a pretty bad cancer. So if a person survives 5 years, what is the probability that she will survive 10 years? So you notice this is a Bayes rule problem because it's asking for conditional probability. So conditioned on the fact that the patient already survived 5 years, what's the probability that the patient's going to survive 10 years? Okay, that's one way of rephrasing the problem. So I'm going to write this in the notation, the Bayes rule notation. So the probability of surviving 10 years given that you've survived 5 years, okay? And so Bayes rule says that we can find the answer by using their handy-dandy formula. Okay, and I can just substitute in these values. So we know this is going to be 0.2, we know this is going to be 0.6, and the probability of surviving 5 years, if you've survived 10 years, of course, is 100%. So 100% times 0.2, or 1 really, times 0.2 divided by 0.6 is going to give us about 33%. So given that you've survived 5 years, the probability that you're going to survive 10 years is 33%. It increases from this number. Okay, so in this third question, on the third homework assignment, we're provided with a table that says responders, non-responders, and test positive, test negative. What is this all about? So basically, there's a new diagnostic test, and to test the parameters of this test, researchers conducted an experiment where there were 59 known non-responders and 72 known responders, and basically they were given this diagnostic test to see how accurate this test was. So this is sort of a typical sensitivity, specificity, positive predictive value type problem. It's important to know before you start these things that if you want to apply the formulas given for, let's say, sensitivity, for example, when given a contingency table like this, if you search for sensitivity on the internet, you're going to see a lot of resources saying sensitivity is simply equal to A over A plus C. And while that is true in this situation, you have to be very careful when applying this formula, because this only works when this is the gold standard, or what's considered true, and this is the diagnostic test. Okay, a lot of times there are 2x2 tables given that have exposure on this side, exposure yes, exposure no, and cases and controls over here. So in that situation, you can't just do A over A plus C as the sensitivity. So first question, what is the sensitivity? So as I said, it's simply 10 over 10 plus 49, okay, 10 over 59, and that's going to be equal to 17%. 17% is the sensitivity. Next part of this question, what's the specificity? Okay, specificity is just this number over the total. So it's 63 over 72, and that's going to be equal to approximately 88%. The specificity of this test is approximately 88%. Then the next part of this question is asking about applying this test to the general population. We know that the prevalence of testing positive for this test is about 50%. So we want to use this information to calculate a positive predictive value. Okay, and so in order to do this, we're going to need to apply Bayes' formula. We cannot calculate the positive predictive value directly from this. Okay, so Bayes' formula can be set up like this. So the probability of being resistant to the antibiotic given the test is positive, okay, equals the probability of testing positive given that you're resistant, okay, multiplied by the probability of being resistant over the probability of testing positive. Great, so we can fill these in. So this is going to just be 17%. We calculated that earlier. This is going to be 50%. This is given in the question stem. We know that the prevalence of resistance among the general population is 50%. And then lastly, this part about the probability of testing positive, well, we can use an expanded formula to calculate that. So that's going to be the sensitivity of the test times the prevalence plus 1 minus the specificity, or 1 minus 0.88 times the prevalence in this test. Okay, so that's just the expanded version of what this is. It's the probability of testing positive in two different situations, okay, applying the sensitivity in 1 minus the specificity. So doing all this out, I'm running out of room here. If you do out this calculation, you're going to get 59%. So the PPV of the test in the specific situation of having a prevalence of resistance of 50% in the general population is 59%. Please note that this value for the PPV is going to change if the prevalence in the general population changes. The next part of this question is asking about the negative predictive value. The prevalence of resistance is still 50% in the general population, but now it's asking us to predict the negative predictive value of the test. And so again, we can't calculate this directly. We're going to use Bayes' rule for this, and we're going to set that up in a similar way. So the probability that the NPV is the probability that you're a responder in this situation, given that the test result is negative. Okay, so if I set that up using Bayes' rule, it's going to look like this. Okay, and we can fill these in with the information we calculated in the earlier parts of this question. So this, of course, is just the specificity. So this is just going to be 0.88. The probability that your responder is given in the question stem, that's going to be 0.5. The probability of having a negative test, again, we're going to use the expanded definition here. What we're going to do is multiply the specificity times the prevalence rate in the population and add that to 1 minus the sensitivity, or 1 minus 0.12. Excuse me, I believe it was 0.17. It's 1 minus 0.17 multiplied by 0.5. Okay, so this is going to give us the probability of testing negative. These represent both situations in which the test would come out negative. So if we multiply all this out, and again I'm out of space, but if you multiply all this out, the NPV works itself out to be approximately 51%. The fourth question is asking about probabilities again. So in a blind taste test, there are 3 panelists that taste 5 different pizza brands, okay? It's not important what brands they are. Let's just say it's a brand A, B, C, D, E. What's the probability that all 3 panelists rate one of these last? Let's say E. So what's the probability that all panelists rate E last purely by chance? Okay, the question says, assume there's no taste difference between the 5 brands, and this is purely due to chance. Okay, well, what's the probability of selecting E among these 5 purely due to chance? It's just 1/5. And for this to happen for all 3 judges, it would have to be 1/5 times 1/5 times 1/5, right? So that's going to lead us to 0.008. Or in other words, 0.8%. So it's very low likelihood that if all of these pizzas were equal, that they would all rate one of them last. So then we move on to the last question in this data set, and this is again another quote-unquote at least type probability problem. So let's keep that in mind as we think about this. So the question starts out by saying that in the early 1980s, patients received reconstituted clotting factor derived from human blood. Okay, the concentrates were pooled from about 1,000 donors per lot. If the prevalence of HIV in this donor blood was about 1 in 3,000, what was the probability that a hemophiliac would contract HIV from a single infusion of clotting factors? Okay, so let me write this out using words first. The probability of having at least one HIV positive transfusion in those sort of 1,000 donor lots is equal to 1 minus the probability of having no HIV positive donors, right? And that makes sense. So you have a lot of chances for having HIV positive, but these are all encapsulated by doing 1 minus the probability of having exactly 0 HIV positive donors. And so what is that probability? So if the prevalence is 1 out of 3,000, then what we can do is do 1 minus 1 out of 3,000, okay, to get the probability of no HIV positive donors. And of course, these are pooled over 1,000 donor lots, so I'm going to raise that to 1,000. And then I'm going to subtract all of that from 1 here to mimic this part of the equation, okay, to get at least the probability of having at least 1 HIV positive donor. So it's 1 minus the quantity 1 minus 1 over 3,000 raised to the 1,000. And that's going to equal 28.4%. And that ends homework 3.